Okay, I am very honored to have invited myself to speak at this conference, and I'm gonna talk is going to be based on some work. Let's see. So this is based on my published work with my former student, who is now a postdoc in Princeton, and some work in progress. So let me first talk about well, the physics motivation. And this is the theory of, well, the motivation originally came from the theory of quantum Hall effect. So in this talk, D is going to be dimension of space, and space-time, and dimension D+1. And what's Hall conductance, first of all? Well, Hall conductance is some quantity from solid-state physics, which measures the skew-symmetric part of the conductivity tensor. And the conductivity tensor is, a very simple thing. If you maybe remember from elementary physics course, that if you something called Ohm's law, which you apply electric field to a material, typically there's current, and they're proportional, and the proportionality is given by some tensor. And this tensor is rank 2 and has symmetric and skew-symmetric part, and the skew-symmetric part is a bit weird, but it has this interesting feature that at low temperatures, it becomes insensitive to variations of pretty much any parameter if the system is insulating. So that's most important fact. And in fact, it's quantized in appropriate units, in some sense that is 2 pi times this quantity is a rational number with a small denominator, or it appears to be. Now, how to explain that? There are different ways to explain this. Well, most hand-waving one uses quantum field theory, and says, well, if you decided to, let's look at the, let's try to describe this response using an effective action, and then electric field can be represented by some one form, the potentials on your space-time. The system is 2D, so in space-time is 3-dimensional, so you get this one form. Let's see, still understand why. So this is A is one form called the gauge field, and turns out if you decide to get this relation as equation of motion, this is the kind of action you need to write down, and the coefficient K is related to the sigma just by this relation. K is 2 pi sigma h. So if you, for some reason, you believe that this coefficient is quantized, that is something of a rational number, then you get the desired answer. That's a very hand-waving explanation, because you need to explain a bunch of other things.
No, but you get integer numbers.
Well, that's a problem. That's part of the problem. So if you want to have an honest quantization, you'll say, well, it's an integer, but an experimental is actually a rational number. So that's one problem. Second, why would you want to? Why quantum field theory? Or especially why write this particular sort of topological term in quantum field theory? There's no particular reason to. Now, but anyway, if proceed, there are similar things in higher dimensions, actually in any even spatial dimension, because then you can write a higher dimensional Chern-Simons action. By the way, I forgot to mention that Chern-Simons action in physics, well, Chern-Simons action is a very famous action, and first appeared in physics in Albert's work from 1978, with a very cryptic title. Could not tell from it that it's about Chern-Simons theory, about something about partition function of a degenerate quadratic functional. Now, so this was about this about the action. This is a quadratic functional. It's quadratic in A, but in higher dimensions, not quadratic. So. Now, anyway, so for n greater than 1, this is some sort of nonlinear response of a system. And again, coefficient K is believed to be a rational number for sort of generic solid-state systems, even though mathematically it would be more natural to say it's an integer. Now, there are also non-abelian generalizations of this. And in that case, you need to replace, if you replace the invariance group U1, which is physically gauge invariance, you can replace with some general compact semi-simple Lie group G. Then instead of coefficient K, the parameter space of this kind of actions is an invariant symmetric polynomial in the Lie algebra of this group. And again, you can describe topological response using some sort of Chern-Simons action. Okay, so that's how physicists usually give a hand-waving explanation of this Hall conductance phenomenon, this quantization. But this is not good enough, because first of all, why is it okay to use quantum field theory? And more specifically, topological quantum field theory, because that's what these actions are. They're topological actions because they don't involve metric. And second, why is this quantity robust and the variation of parameters of the system? In particular, why is it maybe rational? but just showing that it's robust would be good enough for many purposes. Rationality is a more subtle issue. Now, and so in this talk, I'm going to explain how to understand something about this problem. The new developments is that the zero temperature Hall conductance is sigma h, and its higher dimensional and non-abelian versions are examples of homotopy invariants of ground states of insulating insulating systems. Well, not really 2D, because 2D is just for Hall conductance. High dimensional just means arbitrary even dimension. And one can give its rigorous definition, but then one needs to work in infinite volume, and one needs to use operator algebraic techniques for that. And you don't need quantum field theory for any of this, so it can be made rigorous. Okay. So first I explained in a sort of more pedestrian way how to extract some invariant of a physical system. So what's our system? Well, the simplest kind of systems in infinite volume are called spin systems on a lattice spin systems. So, and this setup is not something new. It's a completely standard setup you can find in many books on quantum statistical mechanics. So the key point is that first you start with some lattice. By lattice, I mean just some maybe hypercubic lattice, Euclidean space with dimension d, or maybe some general Delaunay subset, just some cloud of points filling out more or less uniformly the whole Euclidean space. Doesn't matter. And you put on every point on this lattice, you put some matrix algebra, endomorphisms of a vector space, of a finite dimensional Hilbert space. And if you take a product of all these matrix algebras and take the norm completion,
almost all factors are 1, yeah?
Yeah, when you take product, you just take a usual tensor product. Yeah.
But
you take this.
Infinitely many, yeah?
Yeah, infinitely many.
I use one. So
yeah, you get star algebra, and then you complete it, and then you get C-star algebra, and it's this kind of simplest type of C-star algebra called uniformly hyperfinite type, and its elements are called quasi-local observables. And then a state on this, such as, well, that's observables of a system, and then you also need a state, and which physically I think is a ground state, just a positive linear functional of unit norm, like in Albert's talk. And then next stage is define dynamics, and for that dynamics is defined by, specify some derivation of this star algebra, C-star algebra. It's an unbounded derivation. And it's not like some random derivation. Typically, physically, you want some special form for this derivation. Sort of, it's an almost inner. It's an infinite sum of inner derivations. So, and these elements hj just live on near some particular sites in a sense. Now, if you get to get something interesting, you need to work with unbounded derivations. So, which don't define some dense domain in this C-star algebra, which causes all kinds of problems in the standard approach. I'll later, in a second, also fix that issue. So, and finally, we're interested in particular kind of states called gapped states. So here's the definition. A gapped state is state which satisfies this. And a more human way to describe this condition is saying, if you use a GNS representation, you could say that if you have a star algebra and state, you can represent the elements of the algebra by bounded operators in Hilbert space using the GNS construction. And then this derivation gives rise to, turns out, typically gives rise to unbounded operator on this Hilbert space called the Hamiltonian. And then on the spectrum of this Hamiltonian to consist of 0 but all other eigenvalues must be greater than delta. That's what it means to have a gapped spectrum.
Here, if you don't do normal completion, consider tensor product, like almost all factors are 1, yeah? Tensor product. Yeah. It will be the same. Does it kind of make sense to just to state on this not completed algebra and write the same inequality?
Yeah, so I mean, it is all these guys, its derivation is defined on such local observables, but it's somehow too small. But A is too big, so there's some intermediate thing, which is where you can work and do physics. So actually, that's what I'm going to explain. So now on this slide, so there's a very natural star subalgebra of almost local observables, which are called well localized or almost localized. It's those quasi-local observables which can be approximated by a local observable on a ball of radius r with a super polynomial accuracy. That is, because the local observable has tails, which can be quite long range. You want to like restrict to those which have some controllable tails. And if you say the tails are exponential, are decay faster than any power of a radius of your ball, then you could say it's almost local observable. It's not a C-star algebra, but it's a Fréchet algebra. It's dense in this standard quasi-local observable. And we should always work with the observables with derivation which preserve this almost local observables. And that makes, all derivation we work with are defined on this common dense domain, and that removes all the most of the issues with the algebra. So you can actually now do algebra. For example, you can now take, say, commutators of unbounded derivations because they do have a common dense domain and get a third derivation. So, all Hamiltonians and general generators of symmetries live in this algebra of nice derivations. Nice meaning have this form where this HJ is not just quasi-local, but actually almost local. They're well localized. So physically, it means that you're working with Hamiltonians or symmetries which have sort of rapidly decaying tails. Okay. And first, also another great thing about this Lie algebra is that you can exponentiate elements of this Lie algebra, and moreover, even paths, continuous path in this Lie algebra. So it's a non-trivial theorem, and it's known as the Lieb-Robinson. Well, it goes related to what's called Lieb-Robinson bounds. Any continuous path of such derivation can be exponentiated to a one-parameter family of automorphism of this Fréchet algebra of almost local observables. So it's as good as behave.
You could see the kind of like on a unitary conjugation in a sense, yeah.
I'm saying if you take commutator.
Commutator, but with real self-adjoint.
Oh yeah, so I forgot to say, yeah. So this guy, yeah. So I want to take a look at self-adjoint elements here. Yeah. So yeah, I usually work actually with reals. So I always look at self-adjoint elements. Actually, my notation, this guy, I forgot to say, is made of self-adjoint elements only. Okay, so and such automorphisms are very special. They preserve locality approximately. I call them locally generated. And these guys, they form a group. And then it's natural to define two states to be sort of in the same phase or the same type physically, if they're connected by such an automorphism. For example, if your state is just a product of states of individual sites, then it's sort of a trivial state, and anything which is related by such automorphisms to such a boring state is said to be in a trivial phase. That sort of gives a definition of a phase of quantum matter on a lattice.
Is it the same that GNS construction can be identified for this?
No, it's no. That sort of equivalence does not mean that the states are unitarily equivalent. So yeah, so that's a that's one thing. So if you try to the most sort of obvious definition of equivalence of states is unitary equivalence, but that's way too fine. So this is a more reasonable definition.
This is another definition of phase where you kind of vary parameters in the Hamiltonian and see when the gap closes. And
yeah, it's actually related to that. So one can show that they're essentially equivalent. Yeah.
That's this in one side this is correct. That's if you have your definition that they are the same GNS space.
No, it's not true. Converse is probably true, but yeah. So these representations, which are equivalent physically, are not unitarily equivalent in general, because this automorphism changes them everywhere, including infinity. It can look, it's not the same. So, so implicitly here, by the way, I'm using metric structure. So when you talk about, say, states of C-star algebras, of uniformly hyperfinite ones, they actually don't carry any information about which dimension you live in. And if you say, well, unitary equivalence is my definition of physical equivalence, again, you don't know anything about the dimension of your space. This kind of definition that I use explicitly puts in metric information that you're living in d-dimensional space. Okay. So finally, I want to discuss symmetries. So a symmetry is simply a homomorphism from an abstract group to the group of these special automorphisms. So this group, abstract group, can be discrete, can be a Lie group, and here I'll focus on Lie groups. And then, of course, we want to define this homomorphism to be smooth a function of parameters. That is, so that makes sense because actually this group of local generated automorphisms is a kind of infinite dimensional Lie group. So it makes so now we know what it means to have a continuous, or have a Lie group symmetry of our system, and we can also say that Hamiltonian is invariant if conjugation leaves it invariant, and a state is invariant if it's left invariant if you compose it with automorphism. Okay, and finally, if you ask, okay, what does it imply for the sort of a generator of the symmetry? Well, it just means that if you have invariance of a state, then the corresponding derivations which generate the symmetries have this property that the average on the value of the state on any observable of this form vanishes. One says that such derivations do not excite the state. So you can think of such derivations as infinitesimal symmetries of your state in the form of Lie subalgebra of this Fresher algebra. And finally, let's specialize to the case of a group being U1. Then there's a single generator called a charge, which exponentiates to identity. And the G-invariant state is simply the one which satisfies this condition for all observables. So in particular, this charge lives in this, it's one of the symmetries, and can further look at derivation which do not excite, which are symmetries of the state, and also commute with this charge. And I call this, this is my notation. U1 invariant derivations which preserve the state. Of course, Q lives in there because it commutes with itself, preserves the state. So that's what I say here. Okay, so for any state with a symmetry, we have this special Lie algebra of derivation which are symmetries of the state and commute with the charge. Okay. And now we'd like to construct some sort of invariant of a state. So before I do that, let me say something about, it's very important to think about locality in this context. What does locality mean on the lattice? Well, first of all, how do we construct invariants before we do that? Well, the only way to construct an invariant, which is a number, is just to take an average of some observable in a state. So now any element of the algebra does define a derivation. They call inner derivation, right? Just by taking commutator. Now, this map from observables to derivations has a kernel made of these scalar observables, but we can sort of restrict to traceless ones because that uniformly hypercoherent algebra has a sort of obvious tracial state, and we can just restrict to those which have zero trace, zero expectation in this special tracial state. And then once you restrict to traceless observables, they just embed into all derivations, so in the form of subalgebra. Well, and one can actually characterize what it means to be inner in a different way. If you take an observable which is local and far from the origin, then its commutator with the well, it's clear in one direction. If you take the almost local observable and take commutator with some local observable, the commutator is going to be very small, like this small, if the local observable is far from the origin. Now, it turns out that the converse is also true. If you have this property, then this derivation is actually inner, has this form. So inner derivation, in other words, simply the one which is localized approximately near the origin, actually any other point, because they're all kind of the same. Okay, so from now on, when I discover some inner derivation, well, I can say, aha, that's in the image, it's then of this form, where B is uniquely fixed if you demand it to be traceless, and then I can take its average. So inner derivations can be averaged in the state. Okay. Okay, now with this preparation, here's the key technical result. Suppose you decompose your lattice into two subsets. And suppose you have some derivation. Then you can always decompose it as a sum of two derivations which are sort of approximately localized on these two sets. That is, the effect on the observable which are far from these sets is very small. Moreover, that's always true for any, that's a state-independent statement. It's kind of trivial statement, actually. But non-trivial part of this theorem is that if omega is gapped and f does not excite the state omega, one can actually choose these two derivations to be also in the same subalgebra, which don't excite the state. So any derivation which is a symmetry of the state, if the state is gapped, can be decomposed into derivations approximately localized in two parts of a lattice, which still preserve the state.
But what kind of subsets you think like even part of the lattice, like half space are not like?
Yeah, I later choose a nice notion, nice subsets for which it's clear what it means, because it's true in general, but in general it's kind of useless. But for nice subsets, it's it's useful. So and furthermore, if everything is U1 invariant, then you can choose these two guys also to be U1 invariant. Okay, and from now on, since I'm going to entirely be working with this Lie subalgebra, I'm just going to denote it D. Okay, so here's finally a definition of a numerical invariant of a two-dimensional gapped state. Okay, so in 2 dimensions, so we have a lattice, which I don't draw, just a bunch of points on a plane, and we have some charge, which is this special derivation. And so we do just take some sort of 3 cones whose union is the whole lattice. And then using that result, you can write the charge as a sum of three charges, which are approximately localized in these regions. And then, and still live in the same, they still don't excite the state, and then you are invariant, and then take the commutators, pairwise commutators. So let's look at their properties. Let's say Q12 is a commutator of Q1 and Q2. Since Q1 is localized on approximately in 1 and Q2 approximately in 2, the commutator is approximately localized near this array 1, 2. That is, if you take observable which is far from this array, the action of this derivation on this observable is going to be very small, like super polynomial is small. So, but let's look at now. On the other hand, Q1 is Q minus Q2 minus Q3, and Q2 commutes with Q, right? Because
why it commutes with Q?
Because I chose them to be in this algebra of U1 invariant observables. Q is a generator of U1 symmetry, so all my this result says that all these guys commute with
So
Q.
commutes with itself. Yeah. Okay.
Yeah. So yeah, and of course Q2 commutes with Q2, and then therefore it's minus Q3. So Q1, 2, in other words, is also localized near 2, 3, this ray. But that means that if something is localized on this ray or near it, and on that ray, it must be localized somewhere near the origin, right? And I said that such things are inner, right? So in other words, so you can average it and get a number. It's actually going to, since my derivation is anti-self-adjoint, then in my convention, then the number is going to be purely imaginary. So if you multiply by minus I get some number, okay? Okay, that seems like pretty a random construction, which shows some random decomposition. Of course, lots of ambiguity in this decomposition. Lots of many different regions you can choose. So what's happening? Well, here's the result. We proved with Sopenko. Actually, this number doesn't depend on any choices except orientation of the Euclidean space. Flip signs of change orientation. It also unchanged under action on the state with these special automorphisms. And in fact, it's proportional to the 0 temperature Hall conductance. So this kind of magic recipe can be generalized to arbitrary Lie groups, and then it takes values in G-invariant quadratic polynomials in the Lie algebra. Quadratic because, well, this procedure uses commutators. And for special classes of states, one can show that this guy is quantized, literally quantized, integral with suitable normalization. So now actually this part is actually can be shown a different way by Hastings and Mikalakis. So this is not a new result in a sense, but we use a very different notion of what special state is. So for they have a different definition of what is special about their states.
But you say that the things could be rational, not only integer.
For special, yeah, for special ones called short-range entangled or something, or invertible. So that's fine, yeah. We believe that actually it's always rational, but we don't know how to show that. Okay, so that's a very hard problem. Now, so next part is going to be sort of well, charitably, you could say we're trying to understand better this weird construction. Uncharitably, we could say we're trying to put some lipstick on a pig. It is it's not really necessary to understand the construction, but with all this formal stuff. But well, you'll be the judge. So, what are the issues? Why I want to have this formal story? Well, first of all, it's not very obvious how to generalize to higher dimensions. And again, you don't need to know the formal story. You can just guess. In our paper, actually, we have we just guess the construction, and but it's better to have some understanding what we're doing. Also, well, now that's a question like that. Why use conical regions like there? And also, why did I choose this particular configuration of regions? Can we get more invariance of states by using different configurations of regions? Okay, so okay, so what was the key point here? So first of all, what is the property that we used actually? Well, first of all, for any region, I sort of implicitly said it already, had this notion of derivation approximately localized in a region. So for any nice region, you can define presumably some notion of a space of derivations localized in a region. It's a subalgebra in this D. And moreover, we use something like this. If your lattice is a union of some of these regions, then in Q is any element in this D, you can use Q as a sum of pieces which are localized on this approximate localized on these subalgebras. Okay, that's one thing we used. Another thing we implicitly used is that this decomposition is unique up to derivations living on sort of generalized intersections of these regions. Okay, so what does it look like to you? Well, it looks like something related to maybe pre-sheaves or sheaves. Especially the fact that you have unions intersection of regions is representing some sheaf somewhere. Actually, the closest analogy is with pre-sheaves and cosheafs, precosheafs and cosheafs. So let me remind you what these are, because maybe not everybody knows. I certainly didn't know what a cosheaf is before.
You said that the decomposition is unique?
No, it's not. But it's unique up to some well-defined ambiguity. Well, it's unique up to something which lives on sort of intersection, whatever that means. I note intersection with this V upside V because well, wedge, because it's not really intersection. We'll see in a second. In a few slides what it is.
Coarse geometry, yeah.
Similar, yeah. It's broken reformulated in terms of coarse geometry. Yeah. So okay, first recall what precosheaf is. So for topological space, a precosheaf is simply a vector space. It's an assignment of a vector space to every open subset, and a linear map from one of these spaces to another for every inclusion of opens. And you have compatibility with the we have two inclusions, then these maps would compose appropriately. For example, a good example of a precosheaf is a space of continuous functions with support in an open set. So we can extend sort of by zero, and that gives you these structure maps. So in this particular case, this map is simply, in this example, this map is actually injective. And such precosheafs are called coflask. And actually, in this talk, all precosheafs are going to be coflask. So it's convenient because then you don't really need to remember these maps. If your f of u is simply a subspace of f of v, then you don't need to remember really these injections. Simplifies notation. Okay, so now what is a cosheaf? Well, it's a precosheaf with sort of Mayer-Vietoris property. If you have two opens and you look at the union, then any element in this vector space can be decomposed into some of these QIs which live in this subspace. Remember, since everything is coflask, so this guy is a subspace here. And moreover, this decomposition is unambiguous up to the following ambiguity. So you can add something which lives and subtract something which lives in sort of intersection subspace. Okay. So that's what a cosheaf is, then roughly speaking. So we can express the exactness of this sequence. And actually, because of coflaskness, you can just add 0. It's still going to be exact. Okay.
You don't want descent for more general covers?
Yeah, so I'm going to use all finite covers only. So that's enough for me. Yeah, so now this is also for topological spaces, but first of all, we're not dealing with topological space, or rather we do, but it's a very boring topological space. In our case, also localization is only approximate. So then we need to understand what we mean by intersection, union, and cover. Now here's an idea learned from some slides by Schapira. So one can organize function, one can sort of use this non-classical notion of topology, which is very useful in analysis, and can allow us to organize functions in a sheaf or a cosheaf if we replace the category of open subsets with some different category with the Grothendieck topology. And you can design this Grothendieck topology to suit your needs. Now, in case of Kashiwara and Schapira, they usually dealt with some growth conditions on functions, so they organize into a sheaf. But then we have decay, functions with decay conditions, then you get a cosheaf. For them, sort of a test function, if you wish. We're dealing with derivation which is supported in a subset, so they sort of decay approximately. They decay away from this subset, so that because if you have a bigger subset, that still works. So we get an injection. So you get a cosheaf, but then you need to formulate first what the right site is. Okay, so now another idea I learned from this slide is, things going to work nicely if you restrict your sets to something, when you construct your site, you need to make some choices. Don't consider arbitrary subsets, but there's some freedom here. But I like this one. Since remember I had these cones, like a nice collection of subsets of lattice is called semilinear subsets. Or more precisely, subsets of the Euclidean space, and then you can intersect with the lattice. So a semilinear set is a subset can be defined using a finite system of linear equations and inequalities. And these are very simple objects. So if you restrict to closed ones, which is sufficient for our purposes, it's the same as a finite union of polyhedra. By polyhedra, I don't mean like compact one. Just by polyhedron, I mean finite intersection of closed half spaces. So it can be like non-compact. Convenient to use this infinitesimetric. And then easy result is if you have a subset, if you denote by UR, the sort of thickening of U, that is all points within distance R from U, then if U is semilinear or a polyhedron, then thickening is also semilinear or polyhedron. And then let's define, we can organize our closed semilinear set into a preordered set, meaning a set with a transitive and reflexive relation. This is the relation. U is less than V if U is included can be included into a thickening of V. Okay.
It's like compact sets will be all equivalent.
Yeah, right.
If these are non-empty.
Non-empty ones. Yeah. So, okay, so that's sort of fuzzy inclusion, if you wish. Now, preordered set is actually just can thought of as a category. So the morphisms from U to V, it's just a single element if U is less or equal than V and is empty otherwise. Now, post sets probably are more familiar than preordered sets because there you impose further condition that if U is less than V and V is less than U, then U is simply equal to V. In a preordered set, that's not the case. It just means that the U and V are isomorphic, but they don't literally have to be the same. So, for example, all, as Maxim just said, all non-empty bounded subsets of Euclidean, semilinear subsets of Euclidean space are isomorphic. For example, cones with different bases in the same vertex are not isomorphic. So lots of isomorphism in this category, but not some interesting category which sort of captures. It actually captures geometry at infinity because this category is actually equivalent to the category of closed polyhedral subsets of the sphere at infinity. And the initial object here is not unique. Any bounded closed semilinear subset, for example, the point 0 is an initial object. They're all isomorphic anyway. Okay, so, and now, okay, now we want to define, turn it to some sort of a site, so with topology, and for that, first of all, it's convenient to make sure that you have, categorically, you got to have coproducts and finite coproducts and finite products. And from the point of view of order theory, coproducts are called joins, lowest or smallest upper bounds, and products are meets or greatest lower bounds.
So can one just replace the conical set containing 0?
You could, but I don't want to break symmetry. Yeah.
Okay, yeah.
Yeah, that's convenient actually. So now, so the coproduct is simply the usual union, but there's also finite product, but it's a bit tricky. Like for polyhedra, just this.
But in terms of again conical subset, it will be just union intersection.
Yeah.
Yeah. Cones containing 0. Yeah.
So okay, so and like finally, a cover which can just define to be any finite collection such that ui less or equal than u, and then u itself is less or equal than sort of union of these guys, generalized unions. Okay, so it's usually something called coherent topology. I already mentioned, so I'll just so this category is actually equivalent to the category of polyhedral subsets with just inclusions as morphisms. That's because of the statement that because a polyhedral subset is just isomorphic to a polyhedral cone with apex at 0. So sheaves and kasheafs on our sides is just sheaves and kasheafs on the side at sphere at infinity. Okay. Now there's something funny though, a little bit funny. See, the empty subset of the sphere corresponds to the sort of any bounded polyhedron in Euclidean space. Now, normally when you talk about topology, Grothendieck topology on the side of open subsets, or maybe some other subsets, you say that empty subset, you allow empty cover the empty subset. Here, well, if you think about from the sphere point of view, yeah, that seems to be the right thing to do too, but from the point of view of Euclidean space, the initial object is not empty. For example, any bounded subset is the initial object, kind of the analog of empty set. It doesn't seem very natural to say that you allow empty cover of something which is not empty. So, and that actually is important, turns out. So we're not going to allow empty covers. So it's not quite the classical topology on the sphere at infinity. Okay. Okay, and here's an important result that the assignment of these derivations approximately supported on U is actually a Flask cosheaf of vector spaces on this side. Okay. And here it's important for this that to use this weird topology because what we assign to the bounded set actually is not 0. It's actually precisely the inner derivations which we assign to that. And that's not the 0 space. So normally when we look at kasheafs or sheaves, they assign 0 vector space to the initial object, which is usually the empty set. Here it's not 0. Okay, so and once you have that, then we say, well, if you have just like for sheaves, you have homological Cech complex for any cover. For cosheafs, or actually any pre-cosheaf, you can define a homological Cech complex. And if it's co-Flask, then the homology is trivial. Well, I sort of augmented it with this f, the whole lattice, so to make it 0, even in degree 0. Okay, now the last thing to use is that we need to understand in what sense Lie algebra structure is compatible with this thing. So far I didn't mention any Lie algebra structure. So here is the interesting thing. So locality can be expressed as the following property, locality of the Lie bracket. If you have commutator of two subspaces, it actually lives in the Lie algebra of this generalized intersection. This is what it means to be local in this sense. And then, in addition, this Cech complex of this cosheaf becomes a one-shifted differential graded Lie algebra. So one-shifted because, this term is in degree 0, this is in degree 1, degree 2, and so forth. Okay. Okay. And let's now recall how to, let's now try to construct the whole conductance again using these notions. And let's do two-dimensional case first. So we have some charge which lives in this Lie algebra attached to the whole lattice. And it's central because by definition of this D, it commutes with everything. So let's pick any cover of this our lattice in this generalized sense. And by the cosheaf property, you can choose a zero chain such that Q decomposes into the sum. And then we'll consider the commutator. It lives in degree, since this is like in a shifted sense, it's Q has degree 1, then P has degree 2. But in the old grading, before shift, it has degree 1. Okay, on the other hand, when you have a cover of your plane, it induces a cover of S1 by closed intervals. Let's take a 1-cut chain of the Cech, homological Cech complex, and then let's do some contraction of my one chain of derivations, and this DGLA, and this 1-cut chain, numerical cut chain. So here is a result that if alpha is a cocycle, and actually, even though Pij are just some derivations supported on non-compact regions, this combination is actually inner. So you can define its average. And then it does not depend on the choice of this cycle Q at all. It doesn't matter how you decompose if you fix the regions. And as for the cover itself, and this cocycle depends on the class of alpha in this direct limit. Now, it's not a big, terribly surprising. This direct limit is actually just the usual singular cohomology of S1. Okay, you're using here closed covers instead of open ones, but it's still true. So, and now we know what this thing is. It's one-dimensional. So, therefore, there's exactly one way to construct a numerical invariant here, namely the one which we already know. So, nothing new. That's what I mean by putting lipstick on a pig, because actually we're not going to get anything new from this. But you can use any cover. It doesn't have to be that one. And also, what it means to decompose. I mean, you can use, for example, this decomposition of a lattice into regions only sort of approximate. You can use big holes, and it's still going to be, be true. Like, for example, I had 3 conical regions, but if you remove some strip out of these regions, it doesn't matter. Nothing will change because sort of fuzzily they still cover the whole lattice.
So P alpha being inner is coming from the assumption of being central Q.
Yes. So P is it's a cycle. It's a cycle because Q is central.
Yeah. Okay.
Yeah. Okay. So now in 2 dimensions is easy enough. How about higher dimensions? Well, this result actually was actually completely general. So it's actually not necessarily. It's not really. Sorry.
Point to the computer, not to.
Yeah. Sorry. Yeah. Actually, was true. So this result actually doesn't depend on being one cocycle or one cycle. It's actually true for general degree. And you can ask, okay, how do you actually make one cycles, or n cycles, say, in this DGLA? Because then I can, if I'm dealing with a high dimensional sphere, I get this. I probably need high dimensional cocycles. But then I need to construct with high-dimensional cycles. How to make cycles? Okay.
So it is a cycle, of course.
Of this DGLA.
It's a cycle.
Yes. But okay, not. Well, first of all, I need, say, k cycles. Suppose I want to look k cycles of this differential gradient, of this homological Cech complex. But also, I want them to get something well defined. I need something which lies in the commutator ideal. On the other hand, if I just take commutator of cycles, that gives me trivial invariant, zero invariant. So basically, I want to construct, I want some way to construct elements of homology of the commutator ideal, which is itself a DGLA. And the only way I know how to do this is in Moore-Cartan equation. I don't know, maybe there's some other ways. So anyway, for example, in our case, we start with we have this special element Q, capital Q, which lives in degree 0. So I add some formal variable of degree -2 and look for solution of this equation. where have a sequence of these chains. Like this lives in Q0, and this degree 2, degree 4, and so forth. So whole G of t has degree -1. So in my convention, when differential decreases degree, this has degree -2. So it's all consistent. Left side has degree -2. This is also degree -2. So I look for solutions of this. You can easily check that this equation has a solution, and moreover, and then we set, then we have just take del of the nth term in this, solution in here. That clearly by the equation, that's actually the kind of thing we want. It's a cycle by the equation. It also lies in the commutator ideal. And then to get, this is what I say here. And to get an inner derivation, just contract this n-1 cycle with n-1 cocycle. And then you get a number by taking the average of that. And then for the same reasons as before, it depends only on the class of this cocycle in this group. But of course, this is non-zero only if n is equal to d. So on the other hand, n was always even right here. So we get one invariant for any even dimension and no invariance for odd dimensions. Okay. So that sort of proves that what we had was the only thing which one can make in this situation. And in an abelian case, we can do a similar thing. You just have more variables. Instead of just one variable degree -2, you have as many variables of degree -2 as the dimension of the Lie algebra. Okay. And then again, that turns your Q, which is now a collection of Qs, into a central element. And then you just run the same machine. Okay, so that's all I want to say, basically. So I just want to first of all say that this is based on some discussions and work with my current and former students, Adam and Bowen, and also with Owen William and Bas Janssens. And last but not least, congratulations, dear Albert, on your 70 years of productive work in math and physics, and hopefully we'll see a lot more. So that's...
Thank you very much. Questions, please.
So I'm just trying to understand this DGD algebra that you construct. Should I think of elements of it as like some point topological defects in your, because they're like symmetries, something like that?
I actually don't have a physical interpretation.
Oh, you don't?
No. I just regard it as purely mathematical construction. So it's natural to... Basically, okay, maybe I should have said it. So the fact... if I could actually localize approximately to regions, so that all these decompose my charge into this in charges on regions, so they all commute, that would mean my symmetry can be sort of gauged, localized completely. Whenever this invariant doesn't vanish, my whole invariant, it means you cannot do it, no matter how you did. There's just no way to localize a symmetry. So the meaning of this invariant, therefore, is just abstraction to sort of localizing a symmetry, even approximately. So that's how I view it physically. As for the way I construct the invariant, I just don't have a physical interpretation, just a mathematical trick relying on the fact that, first of all, I have a cosheaf of Lie algebras, and second, have this property that the Lie bracket is local, so the commutator on two regions lives on the intersection of regions. So that's all. And that's how I get DGLA. And that's not physics, though, it's just math.
Other questions?
I have a remark. It seems that what is considered here is a kind of theory of physical systems that have a kind of locality which is not locality really, which some generalized locality. This can be understood if you have translations. Then this can be understood in the sense of asymptotic commutativity. But here the translations are used. And so that's, it seems that there is an interesting problem to really analyze this system with such weak locality. That's, I believe, this interesting problem.
Yeah, so I think, yeah, just a remark, but I'm just saying that I'm not sure. So yeah. So the point is that in lattice systems, if you require strict locality, you get nothing interesting. There are no interesting symmetries of states with strict locality. They're just too strong to demand just your derivation to just literally live in some subset. So that's why basically we had to develop this theory of approximate locality. And it's interesting. So from my point of view, just a way to mimic true locality in field theory on the level of lattice systems. So that's how I view these constructions. So in field theory, you can probably not use this strange notion of locality, but just work with localities people usually work with. Yeah.
Yes, please.
Could we go back to the slide of more Cartan, please? The question. Why is it like you take monomial as coefficient?
Well, again, I don't have just my problem is really the problem I want to solve is just to construct homology elements of the homology group of commutator DGLA. So if you have DGLA, you can take its commutator ideal. It's also DGLA, so you can take its homology. Now I want to construct some elements there. I don't know how to do it in general, but this is sort of, how I do it because that again, there's some guesswork here. Like, why do I do this? I don't know why I do this. So, it's just because it works.
Why this equation has solution?
It's because of this.
Step by step.
Because it's a cyclicity of this DGLA gives you a solution. Yeah.
So basically, because you want to relate your DGLA to this equation appears because you want to calculate some chain complex or something. How this appears?
Is there like a shock here? So, thank you. So I have this DGLA D of Cech complex of this D with respect to some cover, and let's call it L. So and then I'll look at this. It's also a DGLA, and I want to compute its homology. So, just of this DGLA. Now, if my DGLA original L has no homology, but this can have homology. So the question is, how do you actually construct elements in there, which in some sense factorial? And I don't know. Any systematic procedure. I mean, I don't know, but this is a procedure which is systematic, starting from some particular element here. Q lives in L, right? Starting from that Q, I can construct what I need, but I don't know if there's some other ways to do it. I don't have an explanation of why this is the right way to do.
So it's just chain complex or homotopy in the homotopy category or in triangular one, just at the level of chain complex.
I just want to say, I look at this DGLA and I want a cycle, and I want cycles. I want the cycles here. I want homology of this DGLA. Okay, and this procedure of passing from L to L, commutator subalgebra doesn't preserve. It's not. It's not invariant quasi-isomorphism. So even though this guy has no homology, it has homology. But I don't know why more Cartan is the way to get cycles in there. It's just the thing which seems to work. Yeah.
Does this have some analog in the continuum, or are you saying it doesn't have? That's the point is that it doesn't have something.
In continuum, probably does. Yeah, I hope so. But continuum, in the continuum, I'm just not sure what's the analog of this DGLA. I mean, this cosheaf of DGLAs. I think there you should probably just have a normal site of opens, or maybe with some finiteness, just allow only finite covers, for example. And then there's some notion of symmetry of some field theory, which is going to give you local symmetries of that symmetry. I'm not sure if that's the right thing, but that seems like a natural way to go.
Yes, please.
So how about the rationality of these whole conductance, understanding, for example, that you get particular rational numbers?
Well, from this you can get that it's robust. It's a real number which is robust. Then if you change your state in a family, it doesn't change in a suitable notion of family, which I define using this locally generated families of automorphisms. Now, why it's rational? We know that for some classes of states, it's integer. Why it's rational in general, we have no idea.
With particular rational numbers?
Well, I mean, experimentally, they're particular rational numbers, but on the other hand, you know, probably if you like go to lower and lower temperature, pretty much every fraction will appear. Every rational number might appear. So it's not really particularly clear that there is some constraint on, say, denominators of this thing.
You say that there is no explanation just from physical viewpoint?
There's no I would say there's no satisfactory explanation. There are some hand-waving explanations, several ones, but kind of hard to take them seriously. So, rationality is a very strong property, which basically physically would follow. Actually, more, even mathematically would follow. For example, this Hastings-Mikalakis proof. If you could show that the number of superselection sectors in this system is finite, it's a finiteness.
But you said that the experimental fact that this conductor is rational. But how can you discriminate a rational number from irrational?
No, you cannot experiment. It looks like. It doesn't mean that it is. It looks like it's very close to rational numbers.
You just measure experimentally something that's just a decimal fraction up to some.
Yeah, it's some fantastically good quantization though. It's very good quantization, like literally many digits of quantization. So it's so good that people use the standard of
rational word rational. So with one particular denominator, because it's
no, that's different kinds of denominators. But for example,
then if it's just set of rational numbers with all possible denominators, they're dense, right?
No, but you know, for any particular say it's not low temperatures. For any particular temperature, you only see a finite number of fractions. And if you lower the temperature, like more, you can see more fractions and so forth, right? So in any experiment, you know, you see only finite of this number of this fractional value. There's a various magnetic field.
So to explain that, you need to use more extra makeup on a pig.
So you need to?
You need to use extra makeup, not only lipstick, on a pig.
Yeah, well, it's a long-standing problem to explain which fractions appear and the order in which they appear. Why certain fractions appear first and others are very difficult to see in experiment. It's not understood. Mathematically, I think it's just a very good problem why it cannot be a rational number. So presumably it comes from the fact that each side is a finite dimensional algebra. Somehow that fact is responsible for the rationality. The fact that if you allowed some infinite C-star algebras on sites, you probably not get that. But there are many, actually that's not the only place where this finiteness plays a role. For example, if you, it's believed that at least in 2 dimensions, unitary TQFTs appear and describe the behavior of the systems. And again, what I mean TQFT? But usually people think that a TQFT has a finite dimensional space of states attached to, say, a torus. Is it true in these systems? Nobody knows, but if it's true, then you can actually deduce rationality of Hall conductance. It follows from Hastings-Mikalakis result. So, but again, it's even harder probably to show that than to show rationality of Hall conductance.
And also there was this very long time ago, so by Billy Sarr.
It's about non-interacting electrons. There it's integral.
No, not fractional.
No.
Sorry, maybe it's stupid question. By experiment, computer experiment.
No, I mean actual experiment. Yeah, actually, quantization of these plateaus in some Hall conductance is very parameters is so good that it's now used in metrology. It's like the standard of resistance.
But is it possible to make also computer experiments?
No.
I think it's harder, yeah.
No, it's not possible because in interacting systems, the cost of simulation is incredibly prohibitive. It's exponential. The dimensional Hilbert space grows exponentially with the number of sites. Just completely out of the question.
So in your previous slides, you asked a question about
maybe quantum computer will help.
Yeah. If you believe in those, yes.
So you ask a question about generalization to higher dimension. Does this answer that question?
Yeah, so that's a systematic way to construct. You said you get one invariant for every even dimensions. Now, by the way, there may be some other entirely different ways to construct invariants. So this is just some particular class type of construction when you use cycles in this DGLA. So that's, I think it closes that type of construction. We know how many invariants we have and when we have them, but maybe some entirely different constructions, which actually we believe that there are. which use some more subtle properties of this algebra.
Let us thank Anton again.
That is my privilege.